Hey, Honors Math 3. Let's talk about some special piecewise functions. So today we're going to be able to analyze, identify, and graph special piecewise functions. So the first one we're going to talk about is the absolute value. Well, we've already talked about that for a whole section, but absolute value can be considered a piecewise function. So it's a special piecewise function in which the graph is a combination of pieces of the line y equals x and y equals negative x. So if we've got a graph, we're going to graph a piece of the line y equals x and a piece of the line y equals negative x. So the absolute value can be written as f of x equals the absolute value of x, like we're used to seeing right here. Or we can write it as a piecewise. So f of x equals x when x is greater than or equal to 0, and f of x equals negative x when x is less than 0. I personally like the absolute value symbol because it's quicker and easier, but you can write it either way. They're both just as correct. All right, now a step function. This might be a new kind of function for you. So a step function is a special piecewise function in which the graph appears to take steps. Imagine that. So here we've got a graph that looks like I'm going upstairs. It's a series of horizontal line segments, increasing or decreasing by a constant. So a step function is not usually written as a regular piecewise function. Since there's so many pieces, it would take a really long time to write. The exception would be if there was a really restricted domain. So if I only wanted to know between x is 0 and x is 3, then you could write it as a piecewise function because that's only 3 pieces. So our step functions are either going to be ceiling or floor functions. The floor function, it's the largest integer, or the whole number, less than or equal to x. It's written as, looks like the absolute value sign with little feet. Floor means I'm rounding down. Ceiling function, it's the smallest integer greater than or equal to x, and it's written as the ceiling of x, which looks like an absolute value with a little ceiling on it. And when you think of a ceiling, you want to think of rounding up. Because if you think about where your head is, your floor, you look down, you round down. You think of a ceiling, you're looking up, you're rounding up. So let's take a look at what this means. So if I have some values for x, the floor of x, I want to round it down to the nearest whole number. Take a look at the number line so we can see where it is. So 4, rounding down to the nearest whole number, that's 4. Rounding up to the nearest whole number, that's also 4 because it's right there at 4. Now everything in between whole numbers, that's where you have to do a little bit of work. So if I'm talking about 0.35, the floor means I'm going to round down. I'm going to go to the left. So that's 0. If I want to round up for the ceiling, then I'm rounding up to 1. 0.99, the floor is still 0, and the ceiling is still 1. So I'm taking wherever I am. Floor, I'm moving to the closest whole number to the left. Ceiling, I'm moving to the closest whole number to the right. So 1.01, here, let's erase that. Those marks. Oh my goodness, sorry about that. Let's erase those. I'm not having good luck here. Well, let's just leave it. All right, so 1.01 is just a little bit above 1. A floor, I'm going to round down to 1. Ceiling, I'm going to round up to 2. So it doesn't matter how close or how far away it is from the whole number, You're still rounding up and down. 1.56 will have the same floor and ceiling as 1.01. Now, negative numbers tend to confuse people. Think about the number line. You're still moving to the left when you're talking about a floor and to the right when you're talking about a ceiling. So the negative 0.2, my floor, I'm still going to round down to the left. And the ceiling, I'm still going to round up to the right. Negative 1.4, same thing. Still going to round down for the floor, so that's negative 2. And round to the right, round up for the ceiling. Okay, so now how do we write these functions? So since the dot of this function is on the left-hand side, so it's colored in on the left-hand side, that means it can equal that number. That means I'm rounding down. So if I'm rounding down, that means it's a floor function. If the solid circle is on the right, that means the number you're rounding up. And when you're rounding up, it's a ceiling function. So what would this function look like? F of x equals 2 times the floor of x. Now when I'm multiplying x squared by 2, what does that do? It stretches it. If I multiply x by 2, what does it do? It changes the slope. So what do you think multiplying 2 by the floor of x is going to be? Since we're multiplying it by 2, we're going to stretch the graph by 2. So I'm going to start in the same spot, but instead of moving up 1, I'm going to move up 2 and over 1. Like my graphs. Isn't that fun? Doesn't take much to amuse me. So up 2 and over 1. But it keeps going to the left of 0 as well. So I would go down 2 and back 1. Down 2 and back 1. So there's the floor of, well, there's 2 times the floor of x. Floor of 2x is something different. 2 times the floor of x is what we have here. So what about this one? If I have f of x equals the floor of x plus 2, again, let's think about what we already know about quadratics and absolute values and lines. When I'm adding something to the outside of the parent function, that's moving the function up and down. So I'm going to do the same thing here. So instead of starting at 0, 0, I'm going to start at 0, 2. I'm moving up 2. And then my slope is still 1, because if there's nothing here, it's implied that there's a 1. So I'm going to move up 1 and over 1. I have to go back as well. So back 1 and down 1. So this is the floor of x plus 2. Now I'm adding 2 on the inside. Think about if this was x plus 2 squared, what do? I'm moving my vertex here. I'm moving my vertex to the left. I can draw here. It's not working very well. So I'm going to do the same thing here. Doesn't matter what function I have. The pieces are all doing the same kind of thing. So it's on the inside of the step function, so I'm going to graph left 2. So instead of starting at 0, 0, I'm going to start at negative 2, 0. But my slope is still 1. So I'm going to go up 1 and over 1. I just figured I'd take less time this time. So that's the floor of x plus 2. Now this one is where it's going to get us. The floor of 2x. So that 2 is on the inside multiplying by x. Let's see what happens. So let's plot some points to help us visualize what's going to happen. So if I have x is 0, I'll plug it into my function. 2 times 0 is 0. Take the floor of that, it's 0. 0.25. So again, I'm going to plug it into my function. 2 times 0.25 is 0.5. Then I take the floor of 0.5, which is 0. Now when x is 0.5, I multiply it by 2. That's 1. The floor of 1 is 1. So you see how we're doing this? So 0.75, I'm going to multiply that by 2. So 0.75 times 2 is 1.5. If I take the floor of that, that's 1. I didn't bother putting in 1 there because that's easy. It's a whole number. So 1.25 times 2 is 2.5. So the floor is 2. 1.5, that's where I'm going to move up to 3. 1.75, still 3. 1.9, it's 3.8. 2 times 1.9 is 3.8. Round down because I'm taking the floor. That's still 3. So now I've got some pieces of this graph that I can plot to help me get a better idea of what this is going to look like. So there's the 0 to 1/2. When x is 0 to 1/2, I'm rounding down. But as soon as I hit this 1x is 1/2, I'm jumping up to 1. As soon as I hit x is 1, I'm jumping up to 2. So what's happening here? I'm only moving over 1/2 and up 1. So when you think about your slope, is how many you're moving up over how many you're moving over. So I'm moving up 1 and I'm moving over 1/2. Think back to your fractions. 1 divided by 1/2 is the same thing as 1 times the reciprocal. So my slope is 2. And that's inside. But my length is cut in half. So it's not just a slope of 2. My length is cut in half. That does correlate to the fact that I have a 2 here. So in 1 unit, I have 2 steps. That's where that 2 comes from, inside here. In 1 unit, I have 2 steps. All right, let's see if I can delete these. I'm not having very good luck with you guys with this. There we are. So my segment lengths are 1/2. There we go. Okay, so let's evaluate. Let's do some examples. If I want to evaluate 4.2, now I have a little hat on here. So that's the ceiling. That means I have to look up to it, so it's the ceiling. So the ceiling of 4.2 means I'm going to go to 4.2. I'm going to round up. It's 5. Negative 2.1. I've got little feet here. That means I have to look down. I'm rounding down. So that's negative 3. I'm moving to the left. Now sketch. X is x minus 1, the floor of x minus 1. But I want it to be between negative 3 and 3. So the first thing I'm going to do is find my starting point. So when x is 0, the floor is going to be, well, I moved it over to the right one. That's what I did. I didn't plug in points on my graph. I'm using the transformations. So since it's x minus 1, my starting point is moving over to the right one. So here's my starting point. So mark your domains. So you can physically mark them or you can mentally mark them. I can equal -3 and I can equal +3. But I don't need to go any farther than that. Then I'm going to finish my graph. So since it's a floor, that means the left-hand side is solid. But what happens here? Because I can equal 3. I don't color this in because that's not the floor of 3. But what happens when x equals 3? So if I plug 3 in for x, 3 minus 1 is 2. Take the floor of 2. There we go. So there's my graph. Let's see if I can get rid of this ink. So now you can see the graph a little better. Oops, my animations are a little off. Sorry about that. So let's choose some values. So here's another way of looking at it. Let's look at some values. So I've marked my domain using the same graph, the same function we just had on slide 11. Let's plug in some points. I'm choosing values right around -3 because that's the end of my domain. I'm choosing values right around +3 because that's the end of my domain. So I'm going to see what's happening right at the end, and then I want to see what's happening in the middle. So let's see if I can get rid of the ink so we can see it, the animations. Here we go. So I'd have -3.1, subtract 1, which is -4.1, then take the floor of it is -5. I don't need it because -3.1 is not part of my domain, but I want to see what's happening there. At -3, I have -3 minus 1, which is -4. Floor of -4 is -4. 2.9 minus 1 is -3.9. I'm rounding down, so I'm going to the left, so the floor is -4. I've already got these in here because my animation's messed up. But what I did, plug in 1. 1 minus 1 is 0. Floor of 0 is 0. 1.5 minus 1 is 1/2. Floor of 1/2 is 0. Then I'm going to look at the upper domain. At 2.9, what am I? 2.9 minus 1 is 1.9. Taking the floor of that is 1. And I have 3 minus 1 is 2. Floor of 2 is 2. So here we are there. And when I plug in 3.1, subtract 1, the floor is 2. So there's that point. And I just fill in everything in between. Okay, please let me know if you've got any questions.